Dear students, today in this fourth lecture of semiconductors, we are going to calculate the whole concentration in Valence band and the Fermi level. Whole concentration in the Valence band. As we know that the number of free electrons per unit volume in an energy range E and E plus T can be written as dN is equal to D of E, F of E, D of E. This relation actually we have calculated in the previous chapter, free electron model. This is known as equation number 1, and here the d of is the density of the states, defined as the total number of allowed electronic states per unit volume in a semiconductor, and f of e is the Fermi distribution function representing the probability of the occupation of the states with energy E. While if we consider the f of E for the electrons, then now the number of holes per unit volume in the energy range E and E plus D can be written as dP. P is the number of holes per unit volume is equal to d of E into 1 minus f of E dE. Actually, if we consider f of E for the electron, then 1 minus f of E. If we consider total concentration is 1, then subtract f of E, the concentration of the electrons from the total, then we can find the concentration of the holes 1 minus f of E for the holes multiplied by d of E, where we have replaced f of E by 1 minus f of E, which represents the probability of an energy state E not be occupied by an electron. That is the probability of finding a hole in the state E. Now, 1 minus f of E is equal to 1 minus 1 over 1 plus exponent of 1 E minus EF by KT is equal to exponent of E minus EF by KT over 1 plus, we have taken the LCM over here, 1 plus exponent of E minus EF by KT, and then we find the this in this way, the 1 minus f of E is equal to this. This diagram we have we can see that the horizontal lines, the lower one is the dashed line is the valence band, and the upper one is the conduction band, and the line upper to the valence band, horizontal line representing the valence band energy, while the lower to the valence conduction band, there is a horizontal line, that is EC, representing the energy of the conduction band, and the EG is the band gap between the two conduction and valence bands. This is the band model of an intrinsic semiconductor. In the valence band, since E very less than EF, valence band actually lies below the Fermi level, the exponential term in the denominator may be neglected in comparison to the unity. Thus, we can say that the dn denominator's term is neglected over here, as the E is less than EF. So dn is equal to 4 pi by h cube 2m raised power 3 by 2 e raised power 1 by 2 f of e dE, and we get 1 minus f of e is equal to approximately exponent of e minus ef by kt. It follows that the probability of finding holes decreases exponentially with increase in the depth into the valence band. Also, the kinetic energy of a hole in the energy state E in the valence band is EV minus E. Actually, EV is less than E. Therefore, the density of the states per unit volume in the valence band can be written as density of d of E is equal to 4 pi by h cube 2 mp steric power 3 by 2 EV minus E raised power 3 1 by 2. MP is the effective mass of the hole in the valence band. Using equation number 3 and equation number 4 in equation 2, and integrating from E is equal to minus infinity to E. EV E is equal to EV, we obtain the whole concentration in the valence band as P is equal to 4 pi by h cube into 2 mp square raised power 3 by 2 integral minus infinity to EV, and EV minus E in power 1 by 2 exponent of E minus EF by KT of dE. Now we get 4 pi by h cube 2 mp steric power 3 by 2 exponent of ev minus ef by kt. Actually we take the here e minus ef, we add plus and add a term in the exponential ev, and we make some we make two part of this exponential term, and one of them exponent of ev minus ef by kt by taking common, and then integral e minus infinity to ev minus e by power 1 by 2 exponent of ev minus ev by kt de. Let ev minus e is equal by kt is equal to x, then de is equal to minus kt dx, and therefore for e is equal to ev, x is equal to 0. Therefore p is equal to 4x by h cube 2 mp steric 3 by 2 exponent of ev minus ef by kt integral infinity to 0 x power 1 by 2 e kt by 1 by 2 e पर minus x into minus kt dx. एक्चुअली जब हमारे पास जो होल है वो ईवी के बराबर एनर्जी रखता होगा तो उस वक्त उसकी कैनेटिक एनर्जी ऑफ द होल नहीं होगी, उससे जब कम एनर्जी होगी तो उसकी कैनेटिक एनर्जी होगी. जिस तरीके से हमारे पास जो था ईसी से ज़्यादा जब कंडक्शन एनर्जी से ज़्यादा एनर्जी इलेक्ट्रॉन की थी तो तब वो उसकी वो कैनेटिक एनर्जी थी. इसी तरीके से जब ईवी के बराबर एनर्जी होगी तो उस टाइम क्या उसकी एनर्जी ज़ीरो होगी. जब उससे कम होगी, मज़ीद उससे कम होगी, तो वो उसकी क्या है कैनेटिक एनर्जी ऑफ द होल्स होगी जो कि माइनस इन्फिनिटी की तरफ जा रही है. तो पी नंबर ऑफ होल्स पी इज इक्वल टू 4 पाई बाई एच क्यूब 2 एम पी स्टैरिक पावर 3 बाई 2 एक्सपोनेंट ऑफ ई वी माइनस सी एफ बाई के टी, और के टी की पावर 3 बाई 2 माइनस के टी एक अंदर था और 1 बाई 2 था, तो ये डेढ़ होके 1 बाई 2 बाहर कॉमन आ गया. इंटीग्रल 0 टू इन्फिनिटी एक्स पर 1 बाई 2 ई रेज पर माइनस एक्स डी एक्स. दिस इज आवर आइडेंटिटी and the value of that integral 0 to infinity x power 1 by 2 e raised power minus is equal to pi by 4 under root. Then we get the p is equal to 4 pi by h cube 2 mp steric kt into power 3 by 2 exponent of ev minus ef by kt pi by 4 power 1 by 2. p is equal to 2 pi mp steric kt by h square 3 by 2. Taking all these things, exponent of minus ef minus ev by kt, or p is equal to nv exponent of minus ef by minus ev by kt, and here nv is equal to 2 into n 2 pi mp steric kt by h square as a whole power 3 by 2 represent the effective density of holes at the valence band edge for silicon. nv is equal to 2.8 into 10 to the power 25 t into t by 300 per 3 by 2 per m cube. सिलिकॉन के लिए जो है एन वी की वैल्यू जो है वो हमारे पास इतनी आती है. तो सिंस एन यहाँ पर क्या है, स्मॉल एंड नंबर ऑफ इलेक्ट्रॉन्स हमारे पास क्या आते हैं, एन सी इफेक्टिव इलेक्ट्रॉन कंसंट्रेशन एट द कंडक्शन बैंड एज एन सी एक्सपोनेंट ऑफ माइनस ई सी माइनस ई एफ बाई के टी. ये हमारे पास हमने पिछला रिलेशन जो निकाला था उससे हमारे पास वैल्यू आई. द इलेक्ट्रॉन एंड होल कंसंट्रेशंस by the equation 8 and previous equation 6 respectively are valid for both intrinsic and extrinsic materials. For intrinsic materials, these equations can also be written as Ni is equal to Nc, because for the intrinsic semiconductors, electrons and hole concentrations are approximately equal. Ni is equal to Nc exponent of minus Ec minus Ei over Kt. तो इस केस में क्या है, जो Ef हमारे पास है वो जनरल फर्मी लेवल हमारे पास आ जाएगा फॉर द इलेक्ट्रॉन्स एंड होल्स फॉर द एन टाइप एंड पी टाइप सेमीकंडक्टर्स. एन आई इज इक्वल टू एन सी एक्सपोनेंट ऑफ माइनस ई सी माइनस ई आई बाई के टी, एंड पी आई इज इक्वल टू एन वी एक्सपोनेंट ऑफ माइनस ई आई माइनस ई वी बाई के टी. तो वेयर द फर्मी लेवल ई एफ हैज़ बीन रिप्लेस्ड बाय द इंट्रिंसिक लेवल ई आई. Fermi level, since electron and hole concentrations are n is equal to nc exponent of minus ec minus ef by kt, while the hole concentration is p is equal to nv exponent of minus ef minus ev by kt. This is equation number 2. For an intrinsic semiconductor, n is equal to p is equal to ni. Therefore from equation 1 and 2 we get both these equations are equal to each other. Nc exponent of minus ec minus ef by kt is equal to nv exponent of minus ef minus ev by kt. By solving these equations we get exponent of nv by nc एक तरफ ले गए हम लोग, और exponent of minus 2 है ef minus ec minus ev by kt. LCM को हम लोग exponent का log ले लिया इसका, और 2 ef minus ec minus ev by kt is equal to log of nv by nc, और ये ई एफ यहाँ से हमारे पास क्या आया, ई एफ या ई आई इज इक्वल टू ई सी प्लस ई वी बाई टू प्लस के टी बाई टू log of n v by n c. As the effective density of states of electrons n c at the conduction band edge, n c is equal to 2 into 2 pi m p m n steric k t by h square raised to power 3 by 2. Question 4, an effective density of holes n c at the Valence band edge n v is equal to 2 pi m p steric k t by h square raised to power 3 by 2. Equation 5, using 5 and 4 and 5 in equation 3, we get the F is equal to EC by EV by 2 plus 3 by 4 KT log of MP steric by Mn steric. Actually, all the other values are cancel each other, and NC by NV now remains only with the replaced with the MP steric over Mn steric. Here MP steric is the effective mass of the holes, while the Mn steric is the effective mass of the electrons. And this is actually positive because the effective mass of the holes is relatively large as compared to the effective mass of the electrons. Effective mass of the holes is actually high because the holes feel some resistance being a part of valence band, and while the electrons are mobile and energetic and in the presence of electric field, the effective mass of the electrons are less as compared to the actual mass of the electrons. Therefore, this term is positive. The effect EF is EC plus EV. It means this is between the middle of the band gap, EC plus EV by 2 for intrinsic semiconductors. At 0 Kelvin, EF is equal to EC plus EV. By using the K is equal to 0, the right term here vanishes, and we get EF is equal to EC plus EV by 2. This is the equation Sammer. The Fermi level lies in the middle of the conduction band and valence band. This is also true at all other temperatures provided MP steric is equal to Mn steric. If effective mass of the hole and effective mass of the electrons are equal each other, then we can say that EF always is EC plus EV by 2. However, in general, MP steric greater than Mn steric, and the Fermi level is raised slightly as T exceeds 0 Kelvin. तो 0 केल्विन से जब टेम्परेचर ऊपर जाता है तो हमारे पास क्या होता है, थोड़ा सा ये मिडिल में नहीं रहता, थोड़ा सा ऊपर कंडक्शन बैंड की तरफ चले जाता है फर्मी लेवल. तो फॉर सिलिकॉन एट 300 केल्विन द इंक्रीज इन फर्मी एनर्जी इज अबाउट 0.01 electron volt only, which may be neglected for all practical purposes.